Last time we talked about planets for the most part, but what we're going to talk about mainly today is some other kinds of things that are in the solar system. And if we have time, depending on how long it takes, we may sweep back in and start talking a little bit more about planets at the end. Okay, so first up, first type of object I want to talk about is this kind of thing right here. Okay? Does anybody know what this is? Does anybody know what these kind of things are called? What's this thing? Like the technical term for this. Yes. Yes. A little bit of a spelling issue, but that's okay. Yeah, these are called asteroids, okay? These are called asteroids, yes. So, what is an asteroid? Okay, what is an asteroid? Like, if you were to tell like a little kid what an asteroid is, what is it? Like, what's the most basic way you could describe what this thing is? Oops. Flying rock. Okay. So, basically, it's a big chunk of solid, right? Specifically, it's a chunk of rock and or metal in space. So it's a chunk of rock and metal in space, okay? Now, there's something very, very, very important here. It's very, very important in that what I just said. So it's a big solid chunk of rock and metal floating around in space. Orbiting the sun, in our case. But there's one type of solid material that it does not have, and that is ice, okay? In order to be classified as an asteroid, you can be made of rock, you can be made of metal, but you can't be made of ice. And I might just say the word rocky to mean rock and metal, but there's definitely no ice in an asteroid, okay? That doesn't mean you can't have a chunk of ice in space. You definitely can, and we do have those in the solar system. And we have things that are just like this, but they have ice mixed in. But if they do have ice, they're not called an asteroid. There's a different name for them, okay? So asteroids have no ice, but they do have rock and metal, okay? Now, a couple of things about them other than that. Are they all this exact shape? Is this the exact, or is every asteroid this exact same shape right here? No, right? No, they're definitely not all this exact same shape, right? So, some of them are much rounder than this. Some of them are much lumpier than this. This one's shaped kind of like, I don't know, like a potato or something, right? There's a lot of them that are close to this shape, but there can be all kinds of lumpy nonsense. But one thing that we have noticed is that the shape of an asteroid, how messed up it is directly tied to its size, okay? So see this one right here? This thing, is this one right here, is this big or small? This thing right here, can you tell if this is a big one or a small one? Let's say compared to a house. Is this thing big or small compared to a house? It's got to be big. And the way we can tell is we can't tell just by looking at the photograph, but if you look down here, a lot of these pictures have a scale on them, right? And so this distance right here is 5 kilometers, okay? This distance right here is 5 kilometers. So that's over a mile right there, okay? That's over a mile wide. Even though it's in kilometers, remember, kilometers are big, right? So this thing is something like maybe 30, 35 kilometers wide. That's a pretty big one. That's a pretty big one right there. It's not the biggest one, but it is pretty big. Let me give you a sense of that scale. A lot of you guys probably know that an asteroid killed the dinosaurs, right? An asteroid killed the dinosaurs, or at least most of them. The asteroid that killed the dinosaurs was about 10 kilometers wide. Okay, so let me pop myself down here. About that wide in this picture, okay? The one that killed the dinosaurs was that size. So this thing is 2 or 3 times the size of the one that killed the dinosaurs, okay? And it's roughly potato size, or shape, right? They get much bigger than this, but they also get much smaller than this. For example, if we look at ones that are a lot smaller, they tend to be much more misshapen. There's a wider range of shapes for the smaller ones. They can be really lumpy. They don't have to be anywhere close to round. But if we get bigger and bigger and bigger and bigger and bigger, the ones that are much bigger than this are almost perfectly round. At least round enough to the human eye that you're going to think that you're looking at basically like a small moon or something, right? And the very biggest asteroid that we have ever found in our solar system, and well, at this point in any solar system, is one called Ceres. I'll write that name down. So Ceres, zoom in. And it is about 300 kilometers wide. And if I showed you a picture of it, you would think you were looking at the moon. Okay? There we go. Oops, this is... Focus. There we go. No, focus. Okay. All right. Now, here's the thing. We've got to come up with a reason for this correlation. So what I'm saying here is that the bigger they are, the rounder they are. Okay? The bigger they are, the rounder they are. And there's got to be a reason for that. And we got to figure it out. Okay? So let's think about this. If we look at bigger and bigger and bigger asteroids, what's probably true about the mass? As the asteroid gets bigger, what's probably true about the mass? Does the mass go up or does the mass go down as asteroids get bigger? Yeah, that one's pretty easy. The mass will go up as the size goes up. When we're talking about rock and metal, if you've got more of it, it's going to have more mass, or a larger mass, okay? But if those bigger ones have more mass, what does that mass create more of? More mass means more what on that asteroid? What does mass create? Gravity, right? So the bigger an asteroid gets, the more gravity it's going to have, okay? So Ceres here is going to have more gravity than this one I showed you a photograph of, okay? And that's the answer to why the bigger ones are rounder, because we typically think of gravity as holding stuff down onto a planet or onto a moon, or in this case, onto an asteroid. But it turns out that an object's gravity doesn't just pull other things, it also pulls itself, okay? It pulls itself, right? So the bigger an asteroid is, the more it tries to squeeze itself with its own gravity, right? And let's think about that. Imagine I gave you a piece of silly putty, or like a piece of clay, okay? And it was just a mess. And I told you, take this piece of clay and squeeze it real tight from every side. Just squeeze it real tight from every side. Squeeze it equally from every side. What shape are you going to turn that clay into if you squeeze it from every side equally? What shape are you going to end up with? Yeah, you're going to turn that piece of clay or that piece of silly putty into a ball, right? It's going to get round. It's going to get spherical, right? So basically, a ball shape is the most compact. So if you're a tiny little asteroid, you don't have very much gravity, so you can't squeeze that rock fully round. But the bigger ones, the ones that are really large, have a lot of gravity, and they can squeeze themselves with their own gravity into that round shape. And that's also why no planets are any other shape, right? All the planets are round. Because compared to an asteroid, what could we say about the gravity of a planet? Compared to an asteroid, how much gravity does a planet have? More or less. Same. What are we doing? Much more, right? Much more. Planets have a lot more gravity than an asteroid, so they're squeezing themselves even tighter. So Earth is round because of Earth's gravity pulling us into a ball. Okay? So that's why there's that correlation. Bigger asteroids are rounder because they have more gravity, because they have more mass. Okay. Now, that said, we said that an asteroid about 10 kilometers wide, right, killed the dinosaurs. Did that asteroid kill just the dinosaurs? Did that asteroid kill just the dinosaurs? Did it just like hate dinosaurs or something? No. It killed a lot more than dinosaurs, right? It killed a lot more than dinosaurs. It killed 70% of all life on the entire planet, give or take a percent. Just rounding there. But here's the thing. Did that asteroid land on 70% of the life on our planet? No, right? It couldn't have landed on everything. So how did that asteroid kill everything? How did that asteroid kill everything? Well, let's think about this. When something that large lands on the Earth, what does it create on the ground? Okay? When something that large lands on the ground, what does it create on the ground? Well, it would produce shockwaves, so there would probably be like massive earthquakes very close to where it landed. But that's not what I'm talking about. I'm talking more basic. A hole in the ground, right? It creates a hole in the ground called a crater, right? It's called a crater. And we'll talk more about craters later, but here's the thing. Yeah, if you were standing where that asteroid landed, you're going to have a bad day, right? You're going to die instantly, okay? And by the way, do any of you guys know where that asteroid landed that killed the dinosaurs and all the other stuff? Does any of you guys know where it was? Put in the chat if you know where it was. I'm going to keep talking about this crater. Yeah, if you were right under it, you're going to die instantly. But even if you were near it, you probably died instantly. Because, as it turns out, when something that big hits the ground, it doesn't just make a hole. It releases a lot of energy in that collision, okay? And some of you guys are saying in Mexico, that is basically correct. We have found evidence of a very, 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 very large crater that underground, essentially, that dates to the time that the dinosaurs died out. And it's partially in Mexico, partially under the Gulf of Mexico. Kind of like, Mexico comes down and it comes into the Yucatan Peninsula. It's on that part of Mexico, the little piece that sticks out over here. Okay? Where exactly it is, I don't know the exact boundaries, but it's roughly around there. But anyway, as I was saying, if you were nearby, that impact is going to release so much energy that it's like tons of atom bombs going off. So much heat and light would come out of that impact that if you were sort of nearby, even if you didn't get hit directly, you would get wiped out by that energy release, the heat and light that were produced by that impact. But even that is not the main thing that killed things, okay? When you create a hole, don't overthink this, what happens to all the stuff that was in the hole, okay? What happens to all the stuff that was in the hole? When you create a hole of any kind, what happens to the stuff that was here? Where is it now? Yeah, it flies out of the hole, right? It gets released into the air. And, you know, if you're making a small hole, it's only going to be up here for a little bit and it just lands next to the hole. But this impact would have released so much energy, or sorry, so much dirt and dust and broken rock into the air that it stayed up in the air for around 100 years. And because of air currents, that dust was carried all the way around the entire planet. And so the entire planet had dust in the sky for over 100 years, or around 100 years-ish. Why is that a problem? That actually right there, that's what ended up causing everything to die. Why is it a problem, though? Why is it a problem to have dust covering a layer of dust in the air all the way around the planet? Why is that an issue? Oops. Document cam. There we go. See if you guys can figure that one out. It's one very basic problem. So things would actually be able to breathe. You guys are pointing out important points. It might make it a little bit harder to breathe if you were actually breathing in that dust. And it could pollute water sources. But way more important than those is if you've got a thick layer of dust in the sky, what's it gonna block? What's it gonna block if you've got this thick layer of dust over the entire sky, over the entire planet? And this is the most important thing right here. It blocks the sun, right? It blocks the sunlight, at least some. It blocked the sunlight enough that plants started to die out and algae started to die out, and things that use photosynthesis to create their energy died out. And why is that a problem? Well, if the plants die out, then everything that eats the plants is going to start dying out. And then anything that eats the things that eats the things that eat the plants will start to die out. And then the stuff that eats that's going to die out. And the stuff that eats that's going to die out. So it just goes right up the food chain to the dinosaurs, right? And to basically almost everything else on the planet. It's like the circle of death, right? It's just the circle of death, like in the Lion King, but in reverse, right? Just take that song, put it into a minor key, you've got the death of the dinosaurs, okay? But here we go. That was if a 10-kilometer wide asteroid hit the Earth.